Alright class, today's video we're going to be looking at how we can apply our kinematic equations to scenarios that involve a little bit more complex motion. One way we can make our scenarios more complex is by adding in more than one object that's moving. So again, just a reminder, anytime we're dealing with kinematics, we have to look at cases in which our acceleration is going to be some sort of constant value. And what we're trying to do here is kind of find some way in which we can link the motion of one object to another. So when we do this, we'll still come up with our kind of table of knowns and unknown values. Right, basically want to figure out how can we describe our initial position, initial velocity, final velocity, acceleration, and then lastly time. So to do this, we have to come up with what we consider to be our coordinate system. Right? What are we calling our origin point? What are we calling the positive direction of motion or the negative direction? And whatever coordinate we choose for object number 1 has to be the same coordinate system we use for object number 2. The other thing is typically we'll have to compare motion of one object to the other. So right, we'll have to link this motion in some way. So the way that we can relate these two, right, typically we'll either do this through knowing maybe they both are traveling for the same amount of time, or maybe we can figure out if one object's traveling 5 seconds longer than the other object. Another way we can think about this is through the position. Right? So maybe they start off at the same location, maybe they meet each other and end up at the same position. Right? Things like that we can help link motion of one object to the second. Now, the scenario we're going to look at is going to deal with a scenario in which we've got two separate objects, but we could also do a similar sort of idea if we have a single object, but their acceleration changes to a constant value. So maybe what we have is our acceleration, maybe it starts off for the first 5 seconds as being a positive 2 meters per second squared. Say we'll go time at 0, and actually let's just say we'll make this actually 2 time at 3 seconds, and then maybe after the 3 seconds maybe we'll go from a time of 3 seconds up to a time of 5 seconds. Or maybe what instead happens is we then have an acceleration that's -1 meters per second squared, right? So it's a big example, right? We have two different accelerations, but it's still the same object. They're just different kind of legs of our motion. Now, if we had an acceleration that is what we call continuously changing, that's when we'd have to use our calculus. We will not be able to use kinematics in that case. So for our example here, we're going to have a car and a train. They're going to be positioned 1,000 meters away from each other, and they're going to be facing each other as they start to move. So our car is being described as moving with a constant velocity. Again, constant velocity just means our acceleration is going to be equal to 0 in this case. And as our car is moving this constant velocity, we're saying at the exact same time, right? So we're going to have the same starting time for each of our objects, is that our train then begins to accelerate from rest at a rate of 0.3 meters per second squared. So we want to know relative to the car's starting position, right, how far has it traveled before it's going to collide with the train. So now that we have our scenario, first thing we have to do is come up with our coordinate system. And for this, just like kind of many kinematic problems we'll see throughout the year, we really have a couple different ways that we can define our coordinate system. We'll go through what the two options look like, how we can set up our tables, but we'll only actually use one coordinate system to solve through the kinematic problem. So the first way we can think about this is if we pretend as if we're some outside secondary observer, and we can think about our car and our train, right, more or less moving along a number line, and they're going to crash. So let's say the car, we want to know how far it travels from its starting position. Let's call the car, we'll make that our origin. So that means that our car is going to be placed at the coordinate x is equal to 0 for its initial position. On the other side of things, where the train starts, right, the train we can say that's going to be at a position of 1,000 meters, because that's how far away from the car it is. And let's just say that our collision, right, maybe they'll take place somewhere between each other. We're calling that a position X. So from this, kind of the way that we have our number line set up, again, the car's at 0, train's over at 1,000, right? Any movement towards the right is going to be positive. Any movement to the left is going to be negative. So thinking about where our car starts, again, the car begins for its initial position at a position of 0 meters. And we know it's going to end up at a position of X. If we want to find the initial velocity of the car, right, we're told that the car is moving at a constant velocity of 6 meters per second. So constant velocity means that both the initial and the final are going to be 6 meters per second. Obviously giving us an acceleration of 0 meters per second squared. If we then think about the train, right, the train is going to have a starting position of 1,000 meters. And since it collides with the car, it's going to be the exact same position as the car, so it's also going to end up at a position along our number line of X. Now, up in the problem, we were told that our train is going to be moving, and we're starting from rest. Again, keyword from rest means we're going to have initial velocity of 0. And we don't really yet know what the speed the train's going to be traveling at as it hits the car, so we'll just say right now that's unknown. But we do know our acceleration is going to be our 0.3 meters per second squared. It's going to be directed towards the left here. All right, so because we're accelerating right to the left, we're getting faster in the negative direction. That's going to result in us having an acceleration that's going to be a negative value. So we'll have negative 0.3 meters per second squared. Again, negative sign comes in because we are speeding up and getting faster while moving left. So again, that's where a negative sign is going to come from, the negative 0.3 meters per second squared acceleration. Now at the time, right, that's going to be something that is currently unknown, but we do know that since the cars and trains start moving at the exact same time, that means that they'll be traveling for the same amount of time as when they end up hitting each other. So we can say we'll have the same time for both the car and the train. So that's one way of kind of setting up our coordinate system. The second way would be then thinking of pretend like you were sitting in the car, right? You're moving forward. Also, you can think about it as if you're sitting in the train's moving forward from your point of view, and figuring out how we can describe our different positions and velocities in those cases. Now, when it comes down to it, it really is kind of personal preference over which of this option 1 or option 2 we'll look at in a moment. Again, if there's one that kind of just makes a bit more intuitive sense to you, I say go with that one. But we can think about this as if we're traveling from the point of view of the car, we want to know how far it moves is ultimately our final answer. So we know the two, again, start out are 1,000 meters apart from each other. Now the car, right, we're going to say it's going to travel this distance x is how far it goes forward. And what that means is that the train instead is then going to be moving through the remaining amount of distance we have. So from the train's point of view, right, the train is going to be moving 1,000 minus x. So the x from the car, the 1,000 minus x from the train. That in total gives us our 1,000 distance separation between the two. So from our table, right, we can think of it as the car starts at a position of 0, and then it's going to move forward until it reaches position x. And again, we still are going to have our same 6 meters per second starting and ending velocity because it's constant. Constant velocity means our acceleration is going to be 0. So in this case, nothing actually really changes on the car's values from our two different coordinate systems, but we find something a little bit different for the train. So the train, right, from its point of view, its starting point, we would call that 0 as well. So the train starting in position 0, but from its vantage point here, right, that green arrow till we get to the crash site, it's going to be moving a distance of 1,000 minus x. That's going to be where it will end up from its point of view. Now our train, again, starts from rest. So just like before, we're going to say that means it has an initial velocity of 0. Again, we don't know how fast it's traveling when it reaches this collision point. And when we think about the acceleration, this is now when we have to kind of be careful of, right, what are we calling the positive direction from the point of view of the train? So we think of the train, right, it sees itself as moving forward, right, we're going forward, we're moving in the positive direction. So the train is basically thinking to itself, right, I start from rest, I start to speed up as I'm going forward. It's going to be a positive 0.3 meters per second squared acceleration. Again, positive because it's going to be speeding up while moving forwards, which we're defining as its positive direction. So again, option number 1, option number 2 really comes down to personal preference. For the sake in terms of setting up our problem here, we're going to go ahead and use this option number 1 information. So we'll be looking at our table on the left. And basically what we have is our job is to figure out what we can do to set up an equation for the car and for the train and see if we can get them to be equal to each other. And then again, sorry, one just last thing though to finish off the option 2 table. Just like before, the amount of time we're traveling for is going to be the same in both. So if I want to come up with an equation of motion for the two objects, right, one thing is I can use our kinematic equation x is equal to x initial plus v initial t plus 1/2 at squared, and apply this equation to the car. And again, we'll do the same thing with the train as well. Again, we're going to be using the option number 1 coordinate system here. So for the car, it's going to end up at this position x. It has initial position of 0. It has an initial velocity of 6 meters per second. We don't know how long it's traveling for, so we'll call that t. And the car is going to have 1/2 times an acceleration of 0 for our constant velocity, multiplied by our unknown time, t squared. So equation for car. Do the same thing for the train, again using same kinematic equation. Instead, our final position is going to be 1,000 meters. Oops, sorry. Its final position, sorry, should actually be our x that we have. So and at coordinate point of x. but its initial position is our 1,000 meter point. We then add to our initial velocity of 0, multiplied by our time, add to then our acceleration of 1/2 times our acceleration of negative 0.3, multiplied by t squared. So what we have here is we have two kinematic equations, and we have two unknown variables, right? We have x is an unknown variable in both of them, and we also have t is an unknown variable in both of them. So from here, really anything we want to do to solve a system's equation works, right? We can use substitution, we can use a combination method, we can plot this and solve for the intersection point. Right? We got a couple different options. This one, the algebra actually isn't too bad if we want to just look for solving for our time for the Akar's equation. So again, our 1/2 times 0 times t squared, that's just going to cancel out. So we can say that the time that we're moving for is going to be x divided by 6. Oops. Right. So we're basically saying, right, we have x is equal to 6t here. If we divide both sides by 6, right, that's how we got our x over 6. Now that we know that our car has been traveling for x over 6 seconds, and we know the train is also traveling for the same amount of time, we can now plug this time in over on the right side. So we're going to have x is going to be equal to 1,000. Our 0 times t is going to cancel out. We're left with 1/2 times negative 0.3 multiplied by x over 6 quantity squared. So one thing we'll notice is that we're going to have a term with x in it, or we're going to have an x squared term. So basically we're setting up a quadratic equation here. So from this quadratic, right, one thing we can use is want to have this in the form of like ax squared plus bx plus c. So the way we can do that is we'll subtract over the x to the right side. But if we look at our 1/2 times negative 0.3 times x over 6 quantity squared, that's going to simplify to about 0.004167 x squared. Again, we're subtracting the x over to the right side, so we'll have minus x here. And then our last term here is going to be plus our 1,000. Again, sorry, I forgot the negative sign in front of our x squared term that we got from the negative 0.03. So this is something that when we're looking at this particular equation, right, we have something that's going to be a quadratic. And again, a couple different options here. We can solve for x. What we can do is plot it, figure out our roots, so where our x-intercepts are. We could use the quadratic formula if we wanted to. So we have a couple different options. Really comes down to personal preference. But if we solve this quadratic using our algebra tools, we're going to get two possible answers. Again, we're going to have 384.4 meters be an option. And then our other mathematical solution here is going to be negative 624.38 meters. Again, since our x was squared, there's two possible mathematical solutions. Now we're looking at these two, right? One of them is going to be the physically correct one. The other one will not make any physical sense. So if we go back up to our number line here, right, our car starts at 0, train starts at 1,000. They move towards each other. Right, so there's really no way for our car and train to collide to the left of where the car started if the car is moving to the right. So basically what this means for us is that our negative value, right, not actually physically possible. This collision will not happen to the left of the car starting point. So the only solution that makes sense would be our 384.4 again. It's somewhere in between our car and our train starting position. So the car is going to have moved 384.4 meters from its starting point when it ends up colliding with the train.